It's the deal, but so what happens when you have two DL or like
Okay.
when you make a tensor
So,
of two DL?
I'm actually this class I'm going to hit a mishmash of topics, just trying to finish a few things off. So I'm shifting topics for the moment, and then I'll come back to whatever I was talking about last time around, which was probably polarization and waves. I'll come back to that. But since I had a natural break, I'm going to do something different now. First of all,
Now for something completely different.
here, I want to put in one place the boundary conditions that would apply to the magnetic fields. And so, this one's always true. And others we have to be a little bit more careful about. But to the best of our knowledge, Gauss's law for magnetism says that the flux through a closed surface is equal to 0. And what this boils down to then is that if I have an interface between two media, got the magnetic field in medium 1, the magnetic field in medium 2, that B1 perpendicular to the surface is equal to B2 perpendicular to the surface. And that follows from Gauss's law for magnetism. There can be no distribution of monopoles along the surface. Okay. And we also have Ampere's law, Ampere-Maxwell, but no mu, 4 pi over c. Thank you. So that B1 parallel to the surface minus B2 parallel to the surface is going to be equal to, I guess I'm going to keep a, that's true. I'll keep the 4 pi over c, but I'm not sure that it belongs there. Surface free current plus bound surface currents for the interface. Okay, so the parallel component's not continuous. It responds to the presence of currents, right? But the magnetic field, the thing that we've been calling the magnetic field, right, is, some people call the other thing the magnetic field, H. But our textbook calls this the magnetic field, and I'm happy with that. Since you were wondering why I said we would call it the magnetic field, right? Anyway, B, the B field includes both free currents and bound currents. And so sometimes applying that boundary condition can be a little bit complicated. I also have for these two materials an H field and an H field, right? And the simplified boundary condition that we'll frequently use because it makes things easier is that H1 parallel to the interface minus H2 parallel to the interface. Oops. Let me think about that. There's no mu in this is equal to K3. And we have H is equal to mu B. I think there's no 4 pi over c here.
There would be a mu naught, so there would be a 4 pi over c.
There is no mu in H.
You said B.
Mu naught?
There's no mu naught in H. H is equal to, B is equal to mu naught H.
Yes, so you wrote H equals mu B.
Oops. That's what you're saying. I took points off of that, or for that on the last exam for most of you. Luckily, I have my degree. And I need to apply a warning here.
Yeah, it can't be, you have to have 4 pi over c there because they have to have the same units, so.
Yes, you're right, this is dimensionless. Do they? I'm not sure. I'd say I get back, actually there should be a new phrase. You're filming me over there, right? Don't turn the camera.
Don't.
Which should be that, in which I say I'll get back to you, but then I forget.
Don't. Please don't.
Good, you kept it pointing to the side. All right. Solving real problems in magnetism is a horror. But there are some simplified things that we can think through that will make life a little bit easier for you later on. And what I'm going to do is take a little bit of time out with a significant detour outside of the textbook into electrical engineering. Because they have ways of addressing magnetic circuits, magnetic circuits that can make life a little bit easier as far as figuring out what's going on. And we are going to employ some overwhelmingly simplifying ideas, but that are going to make calculation, straightforward calculation, easy. And then it turns out that we can end up getting an answer to within a few percent relatively easily using these overwhelmingly simplified ideas. All right. First, this one's not an overwhelming simplification. It's that in dealing with magnetic circuits, we're going to assume that V is equal to mu. Doesn't necessarily have to be completely linear, but it does have to have a VH response that starts at zero, and then is single valued. Right? The problem is that with real materials, ferromagnetic materials, when I get up to here and then I take my current back down, because H is really only responding to the current that's creating the field. So H, if I had a multi-loop coil, and I'll make this simplification in a few minutes, would be 4 pi over C N I for that coil, right? So H is just a measure of how much current you're driving through a coil around a circuit, for example. So this is completely reversible. We can take the current up, take the current down. But as I take the current back down, it could turn out that I have oriented domains in the ferromagnetic material, in iron, for example. And the magnetic field doesn't come all the way back down to zero. And then I continue through here. Magnetic field does not become zero until I am driving significantly in the opposite direction. And then it continues down like that. And then as I bring my current back again, I end up with something that looks like that. We can deal with this in magnetic circuits, but we're not going to in this course. What we're going to do is say, we're going to limit ourselves to a material that responds to the magnetic field. And in the simplest case, it would just be a linear response, and that would be great. Right? But it doesn't have to be linear, it can be a little bit nonlinear. But I need to be able to write that. And if I have hysteresis, I can't write that as a simple function. Okay? But I'm going to make a further assumption in order to work with magnetic circuits. Is that I'm going to say that mu is much, much greater than 1. For typical materials, magnetic materials that we're interested in, mu will be somewhere between 1,000 and 200,000. So it's greater than 1.
Just by a little bit.
Here's an assumption that we're going to make, which is not true at all, but is quite reasonable and allows us to do calculations. And that is that across any interface, or actually across the cross-section of a material. So the simplest case would be now that I put something in there, right? What we're going to assume is that B is uniform across the whole cross-section. So that the flux of B through a cross-sectional area is just going to be equal to B times the area. That's a big assumption. It's not necessarily true. It's not true for most interesting circuits, but we're going to make that assumption anyway in order to simplify things. What that really boils down to is that in the types of materials that we're going to be working with, the types of structures that we'll work with, that the cross-sectional area is small compared to the overall length of the device. Embedded in this is the idea that the B field stays in the material. That's a bad way of putting it. Does not leak out of the sides. I think I should probably show you what kind of devices we're typically talking about as being able to solve here. And that would be something like this. An iron core, so I've made a toroidal iron core here, right? Or some other magnetic material, anything that has a large mu will do, right? Something like cast iron works fairly well because it's impure, it's got some impurities, and as a result, it doesn't have large domains that are easy to turn. And mu is around 1,000 or 2,000. But it doesn't retain the magnetization. It would be like, maybe some of you have done this, you know, like you have like a nail, and the nail, you just hold it to a magnet. It is magnetized to the magnet, but then you pull it back off and it doesn't have any remnant magnetic field when you pull it back off. So that would be a good example. Impure iron. Very pure iron, it turns out, has domains that stay in place. Magnetization. So what I'm saying here is that because mu is large, the magnetic field is going to stay in the material. It does not exit the material. And then a related statement here is that we actually know, we have some idea as to what's going to happen here. The magnetic field is going to do something like this. We're going to ignore that. And we're going to say, yeah, it's doing that. It's not bulging out. It's staying in that area. And because I've made that assumption, and because of my boundary condition over here, then that means that at any surfaces, the magnetic field, let's say in here, let's call that core material. The magnetic flux, rather, is equal to the magnetic flux in the gap. And I could put another magnetic material in there, and it would just change the mu of the material, right? Those are the kinds of things, these are the kinds of structures that we can deal with magnetic circuits. Yeah, Jesse.
So are we assuming that like the gap is closed basically, but like it's not really there?
The gap is small compared to the
Okay.
diameter of the cross-section of the area.
Okay.
And thus we can.
Right, yes, we are assuming that.
Okay.
Otherwise, we can't use all the simplifications that I'm going to use for analyzing circuits.
Mhm.
And then you have to employ the full machinery. Yeah.
When you insert something in there that has a different view,
Yeah.
how does the flux stay the same if the mu is much smaller or even linear?
Must stay the same.
Okay. Just the conditions that we put that apply on.
No. Gauss's law for magnetism. What goes in goes out. It must be the same. That is actually the critical
Mhm.
fact, all right? But what we're saying is it's not bulging out, and
Okay.
that's not necessarily true. Yeah.
So if you put in a material with a different mu, would the magnitude of the magnetic field should the entire thing change
No.
from the equal
Okay, so now we're going to do that.
Okay.
All right. Let's see. Aside from factors of 4 pi over c, which I have probably dropped, okay? And I actually, I confess, the problem here is that the references that I use to reteach myself this stuff are all in MKS units. So there's mu naughts and epsilon naughts all over the place. And I attempted to do my best to translate this into Ohanian speak, but I have failed. So you're going to get the key idea, and I can definitely give you the correct equations in MKS, but probably the CGS equations that I'm writing up here are not going to be true. And I'm saying that because I'm about to write something that goes against what Ryan just corrected me on. But because I did everything else without that correction, I'm just going to work through, and then at the end, like theoretical physicists, we're going to look at it and say, oh, the dimensions have to be this, and we'll put in a 4 pi over c where necessary. Yeah.
In reality, when people do experimental work with magnetic material like this, do they traditionally use MKS or CGS for doing the calculation?
MKS, always.
So why are we being taught it in CGS?
And we use, because those are God's units.
I'm a Jew, I didn't know that. Okay,
let me say why they are God's units, okay?
Because the Ohanian said so?
It's
fell.
Oh.
because if you look at Coulomb fields, I've sort of gone through this, but I'm going to re-say it. If you start with the Coulomb field, and then you say, okay, now let's see what happens when we move relative to that field. It turns out that the Coulomb field that you had, the electric field that you had, just naturally transforms into this other electric field that is at right angles to the field that you originally had, creating forces, right? And we, I said not at right angles, it actually transforms into another electric field which gives us a force, right? Everything changes. And one way of describing that is to say that we've got this thing that's called a magnetic field, which is the result of the relativistic transformation of the electric field. But then, if you start with the magnetic field from currents, and then transform that, you get an electric field. So the two things are really completely equivalent when you look at them from the point of view of special relativity. You can completely transform, almost completely, transform one into the other just by changing a frame of reference. Okay? And that would indicate that it would make sense if we treat electric fields and magnetic fields on a fully equivalent theoretical basis, using the same units for both fields. MKS units didn't come about from that point of view. MKS units came about from this recognition that a current gives rise to a magnetic field. And then actually, then we have magnetic forces between two wires. And it was easy for us to measure the current and measure the forces. So MKS units are actually all derived from the idea of the current as being a meaningful thing, right? And then separately, we had circuits with volts and amps and ohms. So we had like two sets of units, and then we've got to figure out how to put these things together. So the amps that went into the MKS magnetic field were deduced from ohms and volts. So you've got, I mean, the system of units is consistent, and it does give you the proper forces as when you do a calculation. But from a philosophical point of view,
They should have the same units.
they should have the same units.
Okay.
But all practical people learned this system and that system. Yeah.
Might have just have done a lot easier and changed the units of charge instead of coulombs if there was maybe something different that would.
I think we would still end up with a dimensional difference between magnetic fields and electric fields. So there is something more fundamental that we have to do there in order to put those two fields on the same footing.
Okay.
So no, yeah, it's not an easy way around this. But to the best of my knowledge, the only people who actually use CGS and Gaussian units are theoretical physicists. And then particle physicists follow along because they work a lot. They work closely with the theorists. And they don't, I mean experimentalists, and they don't want to feel stupid compared to the theorists who are busily using God's units. So I think it's a sociology thing after that. Yeah.
Who uses natural units?
Let's see, natural units are ones where everything's one.
Cosmologists.
Those are the cleverest theoretical physicists. And that's in large part because you do the whole calculation without knowing what any of the units are. And then when you're done, you look at it and you say, okay, I need to have a speed of light and I need to have this and that in there. And you make everything work out dimensionally. And by the time you fixed all the dimensions, you've got the correct conversion factors. And you just save all the conversions until later. And you have to be fairly clever.
That sounds like a really fun
In
idea.
order to do that. Okay, that was a waste of time. So where was I? Yes. So now, with this circuit here, in order to figure out what's going on, what I want to do is employ my boundary conditions, employ the idea that the flux is conserved through the whole structure, that it doesn't bulge out at the gap, which is not completely true. The gap's got to be very small in order for it not to bulge out. But this problem is not trivial because the H field the magnitude of the H field around the structure is going to be what determines what the B field is. And it's the B field that's continuous across the gap. H is not continuous, necessarily. Yeah, H is not continuous across the gap. Let me just say that right away. Okay, but what do I know? And now it comes back to probably I could get away with saying yes. The disclaimer for Ryan. The McAvoy disclaimer. I can do a loop integral of H, and I know that that's going to have to be equal to, that will, let's say over any region here, and here's somewhere where I'm about to cheat with the constancy across the cross-section. Along any region here, that line integral, let's say I go down the middle, is going to be the length of the region, L, times the magnitude of H in that region. So I've got L in the length of that region and the magnitude of H. Now, the problem here is that the length varies from one side to the other. We're going to ignore that. So the cross-section's got to be small compared to the overall diameter of the circuit.
How much stuff are we ignoring?
What?
How much stuff are we ignoring?
We are ignoring this much. In fact, actually, for this lecture, this is where the hands come in handy. I started out with the lecture with just like this. You know. At this point now, I've made a lot of approximations. And it's going to get worse. But then it'll get easier. All right.
Does it all factor out in the end and eventually, I mean,
No.
oh,
This is just an
All the
approximate.
little approximations that we're doing here, they screw us up all the way down the line.
ah,
But if we're just sort of okay with the number being about this, because we're just trying to get an idea of how the system behaves, we're good.
How many astronomers are in the room?
Is that like a trick question?
It was a joke.
It was hilarious.
Because they're what?
very
Off by a
accurate.
factor of 100? It's okay.
Oh. All right.
Off by a factor of 100.
So, for a little segment, actually, let me not do that. For a little bit that I'm going to go from one place to another. This would just be the length of that little region times h for that little region. Now when I go all the way around the loop, now I'll close the loop, erasing that, but I'll come back to it. I'm going to go all the way around, all right? In that case, H is only going to be due to the presence of the current. So I could do something like that and do Ampere's law for that little bit there that encloses all of the current, right? And so that's just equal to the number of turns times the current in the loop times perhaps 4 pi over c.
That's all the free current.
Okay? Perhaps. But this is the idea. Now I'm going to finesse this by calling that, I love this word, EM is equal to, they use this word, and I think you should just, like throw it down at dinner during the summer.
I can do that.
Oh, the magnetomotive force.
It's like the electromotive force.
So I've got a circuit now. I've got a circuit, and the magnetomotive force for this circuit is whatever N times I is for this battery for the circuit, let's say. The thing that is actually creating the fields in the circuit. Yeah, so we have some really bad analogies here, but they're useful. They're actually going to work. So that means then, get rid of the real physics over here.
Okay, we're just gonna toss that out the window.
We're doing engineering now.
Oh, that hurts. That actually hurts.
Ian was ever right? But that's also equal to that. This is sort of neat. The sum around the loop times the H field in each element of the loop. The H is not constant around the loop, right? B is going to be, but H is not. Times L sub I. Okay, now, because of that assumption that I made about the B field, that the flux, I didn't say, actually, I said B was constant. B is not constant necessarily. But the flux enclosed by some surface that brings this whole thing very close to the surface of the magnetic material. That's going to be constant, right? So what I want to do now is sort of try to rewrite this using the flux. Because I don't know what H is anymore.